All right, it is my great pleasure to introduce Professor Jitendra Malik. He's joining us from the Electrical Engineering and Computer Science Department at UC Berkeley. And he is also a part-time research scientist and director at FAIR. He has done a lot of foundational work in computer vision, computer graphics, machine learning, and robotics. He's graduated a whole bunch of very famous people whom you may know. And really, I'm going to cut my bio short and get the talk going. We're already behind. Thank you so much.
So the title of my talk is When Will We Have Intelligent Home Robots? So it's an intentionally provocative title. And mostly it's going to be what work we have done to advance this grand goal. And I'll have a slide at the end which tries to answer this question. Okay, so I always like to state my credo first. What do I believe in? So I believe that intelligence is best viewed as something embodied, something which is the result of evolution. And if we think of it that way, then the starting point of intelligence is sensory motor. You have these animals that could move and they could see. And seeing gave them a benefit because it told them where to go for food. And moving was essential to go get there. So the task of moving and the task of seeing, they go together. One doesn't give you a benefit without the other. And there is this line from Gibson, we see in order to move and we move in order to see. So I think of this as the essence of intelligence. So to make it more precise, there is locomotion and then there is perceptually guided navigation. These are the central problems. And then if we continue on to modern, the emergence of modern humans from branching off from the apes, then we can talk about the evolution of manipulation and tool building and so forth. So once we started to develop bipedalism, our hands were free, and so we could use them in various ways. And that's, of course, and there's this great quote from Anaxagoras. It is because of his being armed with hands that man is the most intelligent animal. And there is very good evidence in the fossil record that the development of the hand precedes the development of the brain. And then in the last million years or so, we have the emergence of language. So in some sense, what I believe are the most important parts of intelligence are the sensory motor aspects. There's locomotion, there's navigation, and then of course there's manipulation. And language is, if we think of this whole period as 24 hours of the development of intelligence, language is in the last 3 or 4 minutes. So in my view, it's slightly wrong-headed to focus so much on language models as the core of intelligence. Language is very important. It's uniquely human. But most of what we will have to solve in robotics will be the central problems of locomotion, navigation, and manipulation. And language models will have a very minor role to play in this. Okay, so let's get on with it. So my talk is organized around these three, what I regard as the three central problems of robotics. So let's start with locomotion. So I'm going to start with this work from a few years ago now. But before I talk about this, I want to make a philosophical remark. So these are some of the learnings that I had when I moved from computer vision to robotics. I've had nearly 40 years in computer vision, and in robotics I've been for maybe 6, 7 years. And a few things that I realized. One was something that all vision people take for granted, which is that we have to solve generalization. So a cat is not one instance of a cat, it's a category, and you have to recognize cats independent of the different kinds of shapes and poses and so on. This is inadequately appreciated in robotics because whenever you do a task in robotics, be it pick up, be it throw, be it insert, it has to be a generalized version of the task rather than a specific instance of the task. I think people are appreciating that in the learning era, but I think to me this is central. Without that, you haven't solved the task. Second point, which was not so obvious from computer vision, but it is central to robotics, is the insight that control theory has given us, which is that we need to be robust to disturbances, and these would be unmodeled disturbances, but so long as they are bounded, then your system should robustly deal with them. So this is central to robotics. And the third point that I wanted to make is adaptation, which is kind of like generalization. So if your robot is walking, it should be able to walk in a variety of terrains. But adaptation gives you a certain sequentiality, which is nice. Because when you're going to walk, when you're going to perform any action, this is going to be over time. So if the situation changes over time gradually, then you can adapt in real time. And this is, I mean, there are areas like adaptive control which have had this insight, but I think this is also central to robotics. So these are some of my philosophical beliefs, and I'll, in this talk about concrete results, but these guide this line of work. So first of all, our work on walking, we started with quadrupeds like some 3-4 years ago, and we trained with reinforcement learning and simulation, and so you get this base policy. But the novelty of our work was this idea that we need to have variations of that base policy for walking in different kinds of terrains, hard ground, sand, etc., etc. And this is captured by this latent Z sub t. This is kind of capturing the environment. And how do we know it? We know it, we have to estimate this online, and we can do that from a longer time history. So while the control loop for controlling the joints has to operate at like 100 hertz, and this policy has to be giving you actions fast, this adaptation from different kinds of terrain can operate slightly more slowly. So maybe it operates at like 5 hertz or something. And it takes you to the longer history of what were the actions you commanded, what was the state that was achieved. So this is the basic idea, and we call this rapid motor adaptation. And this enabled us to train with in simulation and then zero shot work in the real world. And what was nice was that this needed no reward hacking. I mean, this is one of the bane or the ugly underbelly of reinforcement learning. You have 15 terms which are crazily put in just to make the thing work. Here, our reward was basically smoothness and minimize energy, and that was all that we needed to do. And then I'll have this little slide which illustrates this adaptation idea. And so basically, this robot is going to walk on this slippery mattress, and then it sort of struggles a bit, and then it recovers. And the secret here is captured in these Z1, Z5 values, which you see in the panel above. And those are kind of the elements of this hidden Z vector. And that is estimated from the previous temporal history of states and actions. And with that, it effectively is implicitly understanding that now it's on slippery ground, so the policy needs to change in some smooth way. And with this policy, we were able to get the robot to work in a wide variety of conditions. And all of this was there's this behavior, like foot tapping behavior, all of this was emergent. And here is the robot walking. And this, by the way, is a blind robot. So the sensing is proprioception. But this adaptation was key. This rapid motor adaptation was the key idea there. And these are just more examples. And in more recent work, I think Ilya Radasovich gave a presentation earlier today. What we can see is that this is I think a core idea, but it can be implemented in various ways. So if you have a transformer which has a higher capacity to be used for outputting the actions, then what you will find in that policy can adapt as it can, like this biped has to be able to walk on flat ground and sloping ground. But what has to happen inside the in-context learning part of the transformer policy is that this difference in terrain has to be sort of identified and dealt with in terms of a change in policy. And you see that with a couple of the neurons which capture whether you are on flat ground or sloping ground, and it also shows up in doing a PC analysis. So I think this idea of adaptation is central, and you need your machinery to provide that. Okay, so this was a blind robot. So what do we need vision for? Well, we need vision for tasks like crossing a river while stepping on stones, climbing up stairs, and so forth. And so we have some results on that, and I'll just show you the video and not talk you through the details. All of this was published 2 years ago, nearly 2 years ago, so it's kind of well known already. But noteworthy here is that the perception is on board. There is nothing known in advance about the environment. The robot sees what it sees and it acts. And I repeat, the training is done in simulation, zero shot, it transfers to the real world, and there is no reward hacking. The terms are fairly straightforward. Smoothness of motion, minimize energy. And it's exactly the same policy. So, I mean, we can make robots walk with MPC controllers, but you need many different controllers for many different scenarios. Here we have exactly one controller. And in the previous work for the blind robots, the same person. Okay, so now we have this ability. So I regard quadruped locomotion as basically a solved problem. I mean, we can do this. We can do this robustly in a wide variety of conditions. We can do it with vision. We can do it without vision. Then what we can do is to move on to more intelligent behaviors on top of this lower layer of walking. And here's was one fun one that we decided to study. And this is essentially this concept of pursuit evasion games. And let me just show you the demo video first. So this dog, if you will, with a camera is chasing the woman. And it's sort of like, you can think of it as a friendly hide and seek game, if you will. If you want to think of it in a more, predator-prey setting, that's perhaps also a possibility. So the way we trained this was also in simulation, and this is zero shot. The key thing was we assumed that there is a lower level policy which can execute on go in a particular direction at a particular speed. So that's now a primitive. And now you have a hierarchical controller. So the one at the higher level is deciding which direction to go at what speed. And that is what is being trained with this pursuit evasion game objective. So let me go back to the previous slide and show what are the interesting things which emerge. For example, there is chasing behavior where you go to where the person will be rather than where the person is now. Okay, that's important. I mean, we all know that when there's this phrase, right? You go to where the puck is, not where it is now. And then you also get like information seeking behavior, and all of this just emerges. I mean, this is one of the beauty of reinforcement learning. When it works, you get these nice emergent behaviors which we can all point out and feel thrilled about. Okay, and then it's robust, and doing it in this two-level way is great. I think that this is of course a very classic idea of hierarchical control. In computer vision, it's the idea of course to find, I mean, this concept is great, and we need to have it. And sometimes it's forgotten in the end-to-end RL world, but I think it's a very basic and good concept. Okay, And now I'll refer to, I'll just quickly go through some of the work on humanoid locomotion. And Ilya gave a talk earlier, so I don't have to go into any details. I'll just zoom through this. So, so in this paper, the idea was to do next token prediction, similar to what is done in language models. But these tokens, of course, now refer to sensing and action. And with these ideas, where you need a bunch of trajectories, and it turns out that you can get trajectories from other controllers, or you can get trajectories, in fact, from mocap or from video. So we can take video data of humans walking, running, etc. We can convert them to 3D humans or 4D humans if you consider time, and then those trajectories can also be input to this, this controller. And these are examples of that. There's some retargeting to be done because the human body is not the same as the humanoid's body. So you have to convert it to what it will be in the body of the robot. Okay, and with this, Ilya was able to get these robust results of walking around in San Francisco. And you can view this, all these trajectories and this next token prediction as a way of pre-training, if you will. In the language community, that's what they do. They have a huge stage of pre-training, and then after that, there is this RLHF stage. So you can kind of imagine that you've got this pre-training on a very large number of trajectories, and now we can proceed further. And the way to proceed further is essentially by using reinforcement learning again on this better representation. And this is a very recent paper. And so essentially you're going to train in simulation on challenging environments. So you can imagine that you could have done RL all the way without this stage of next token prediction, but then the sample complexity would be much too high, and you might have to resort to various kinds of reward shaping. But these are the results. So I think, so these are various hiking trails around Berkeley. And now to more urban, these are really steep streets in San Francisco. So I don't know if there is any, humanoids are now very popular. There's a lot of humanoid research going on, a lot of companies and commercial interest. But I don't know if there are any really as robust walking humanoid results around. I'd be happy to learn of any where such a wide variety of walking around in such a wide variety of terrain has been demonstrated. Okay, next, let me turn to the navigation problem, because when you want to, locomotion is about the ability to walk, but walking is of no use if you don't know where to go. So often we have some goal. We want to go to the nearby Starbucks, or you want to escape the tiger or whatever. So navigation, this is, I think, central. And navigation, of course, is a classic problem in robotics. Here's a very classic formulation, which is from the era where perception and action were kind of factorized. And I don't fully believe in that. So the job of perception was, okay, run a SLAM algorithm, reconstruct the whole world, and then after that, it's a motion planning problem. And in the last 6, 7, 8 years, so this was the first problem I got into when I got into robotics. And our starting observation was, you clearly do not need a full 3D mapping of the world in order to, find a way out of the door of your room. So, and of course, if you look at the literature in psychology, it's very rich. So there is literature on map building, and that rats build maps, and these ideas have actually led to Nobel Prizes and so on. But there are also works which show that, in fact, the map is kind of incomplete and very partial, and a map is built up over time. So initially, the knowledge is more about paths that you can take and have landmarks. And these are some classic results which show that, for example, animals use both landmarks, and the maps are kind of not complete maps. They're very partial maps, if you will. So we can take these ideas and apply them in robotics. And the problem we are trying to solve is quite, I mean, the previous talk from Bernadette Boucher was very much on the same theme. So what I'm going to do is I'm just going to play a video which shows our results. So this is we have a series of papers. This is the most recent one, which was presented at RSS. And the challenge that we tackled was the following. Okay, you want to be able to navigate in an unknown environment? Okay, what's an unknown environment? Just rent an Airbnb. So what we did was we would rent Airbnbs, open the door, put down the robot, and then give the robot a task like find the TV or find the potted plant or find the green elephant or whatever. And then it succeeds quite well at the task. So I have this 8-minute video which I'll just play, and then when we return from that video, I'm going to talk about some results and manipulation.
In this paper, we present the GoToAnything agent, the first lifelong learning agent capable of multitask navigation to objects, however they're specified. GOAT is the first universal navigation system that can search for and navigate to any object specified as an image, language, or a category in completely unseen environments, without requiring any pre-computed maps or locations of objects. Here you can see it look for a sync image, language describing a teddy bear, and language describing a cup. First, let's discuss the problem we tackle. Imagine dropping a robot in an unknown home and asking it to tidy up. For example, it might have to bring the child's teddy bear to the kitchen chair. What makes this challenging? The robot needs to explore the environment, detect and localize relevant objects, remember object locations to be able to come back to them, and navigate to, pick, or place objects. In any deployment setting, a general navigation primitive should be multimodal. The robot should be able to reach any object specified in any way, as an image, language, or a category. And should be lifelong, meaning the robot should remember object locations and be able to navigate to multiple goals in a row. Let's step through an overview of our system. As the agent moves through this scene, the perception system processes RGBD camera inputs to detect object instances and localize them into a top-down semantic map of the scene. In addition to the semantic map, GOAT maintains an object instance memory that localizes individual instances of object categories in the map and stores images in which each instance has been viewed. This memory allows the agent to localize and navigate to any object instances that have been observed previously. A global policy takes this lifelong memory representation and a goal object specified as language, an image, or a category, and outputs a long-term goal in the map. Finally, a local policy plans a trajectory to achieve this long-term goal and outputs actions to be taken by the agent. Next, let's talk about the perception system. The perception system takes as input the current depth image, RGB image, and pose reading from onboard sensors. It uses off-the-shelf models to segment instances in the RGB image and estimate depth to fill in holes for reflective objects in raw sensor readings. Object detections are then projected and added to a top-down map of the scene. For each object detected, we also store the image in which the object was detected as part of the object instance memory. Let's discuss this memory in more detail. Our object instance memory clusters object detections across time into instances using their location in the top-down map and their category. Each object instance is associated with the images in which it has been viewed. When a new goal is specified to the agent, first, the agent searches the object instance memory to see if the goal has already been observed. The method for computing matches is tailored to the modality of the goal specification. After an instance is selected, its stored location in the top-down map is used as a long-term point navigation goal. If no instance is localized, the global policy outputs an exploration goal. We use frontier-based exploration, which selects the closest unexplored region as the goal. The local policy simply uses the fast-marching method to compute actions that move the agent closer to the long-term goal. Now, let's look at our results. We evaluate GOAT in the wild, in 9 unseen rented homes without pre-computed maps or locations of objects. We evaluate 4 methods, GOAT and 3 baselines, for 10 trajectories per home, with 5 to 10 goals per trajectory, for a total of 90 hours of experiments. In total, this represents over 200 different object instances represented as image, language, or category goals. Let's look at a full episode of the GOAT policy in an unseen home. Here, we show the first-person observation from the robot along with the third-person view. Here, we show the current goal, which is an image of the kitchen sink. The semantic map that is being built over the course of the episode is shown here, along with the legend indicating the recognized instances. Initially, since the goal has not been found, the agent begins exploring. As it moves around the scene, observed objects are added to the instance memory and the map. Every new instance that is observed is compared against the goal image for a match. Once the sink has been seen, it is correctly matched and the agent navigates to it directly. After reaching the first goal, the agent must reach a new goal, in this case, natural language describing a teddy bear. When presented with a new goal, it first searches the instance memory for existing matches. If none are found, it begins exploring. For this goal, the image of the couch, the agent finds a match against previously observed instances, so it can navigate directly to the goal without exploring. Following this procedure, GOAT is able to successfully reach all goals specified in this episode. And here we show the GOAT agent operating in a different unseen home. We compare approaches in terms of success rate per goal within a limited budget of 300 robot actions, and success weighted by path length, or SPL, a measure of path efficiency. GOAT reaches 83% success rate and 0.64 SPL. When removing the persistent memory, success rate drops to 61% and SPL to only 0.19, as the agent needs to re-explore the environment with every goal. When removing the ability to distinguish different object instances from the same category, success rate drops to 49% and SPL to 0.4. When using clip features of entire images to localize goals, as suggested in prior work, success rate is 51% and SPL is 0.42. Additionally, GOAT performance improves with experience in the environment, going from a 60% success rate and 0.2 SPL at the first goal to a 90% success rate, 0.8 SPL, for goals 5 through 10 after thorough exploration. Conversely, GOAT without memory shows no improvement from experience, while clip-on wheels benefits but plateaus at much lower performance. In the same scene with the same goals, we see that our system performs more accurate matching than baselines. And the use of instance memory allows effective localization of previously observed objects, where baselines with no memory can repeatedly explore the same area. This leads to robust and efficient navigation in the real world. As a general navigation primitive, the GOAT policy can be applied to downstream tasks like pick and place and social navigation in a platform-agnostic manner. Here, you can see the GOAT policy search for a bed, look for an image of a specific teddy bear, and bring it to the already localized bed. Here, you can see the GOAT policy plan around a person to reach the refrigerator. Then remove the previous location of the person from the map after the person is moved. It successfully follows the person while updating their location. And finally, GOAT can easily be deployed on many different robotic platforms. In summary, we present the first universal navigation system able to search for and navigate to any object specified as an image, language, or a category in a lifelong setting, in completely unseen environments. GOAT can readily be deployed for pick and place or social navigation in a platform-agnostic manner. Thank you for watching. For more details, please visit the project webpage. In this paper, we present the go-to-anything agent, the first live.
Okay, so now let's move on to manipulation. So I regard navigation as not fully solved, but substantially solved, at least in these indoor settings. The failure cases are often to do not with the map building and so forth, but the vision system, where we are relying on and the state of the art in these quote foundation models for vision is just getting better all the time, and I think that you can just expect that work to take care of the remaining percentage of improvement. Outdoor navigation over a very large scale, I think that's still a challenging problem on which people need to keep working. Okay, now I'll turn to manipulation, and I'll start with one specific case. But first, I'll state some philosophy. So, for me, manipulation is a very broad definition, all the things that humans can do with their hands, one hand, two hands, and so on. And basically, this is, I believe, in multi-fingered hands and with tactile sensing, and that's the generality that is needed for solving general manipulation tasks. So I know there'll be people who will argue that, oh, I can do everything with a parallel jaw gripper, but I think that this is just a philosophical difference. I think for me, the problems of interest to me require that generality. So this is work which is on in-hand object rotation. So the problem is shown here. Well, okay, you'll see the results, but basically there's a multi-fingered hand, and what you're doing is rotating an object in the hand, and the object could be one of many possible objects. And it turns out that you want to have sensing for this. It's too hard a task to be done from proprioception alone. And the sensing here is a camera looking at the object and estimating its shape, as well as tactile sensing on the fingertips. And at the right, you can see what the tactile images look like. And this is what the task is. So what you have in each row is rotation about a different axis. And notice the generalization across different objects, and it's one policy for, okay. So let's see how the system works. So the top row is rotation about the x-axis. This is quite a challenging task. The second row is rotation about the y-axis, and then the third row is about the z-axis, the vertical axis aligned with gravity. And then the bottom row shows that you can rotate about an arbitrary axis. Okay, so what are the interesting things here? Again, we trained fully in simulation and then transferred to real reinforcement learning. Again, there's not too much reward hacking going on. We use the best vision tools, which is that you use an RGBT sensor, you use segment anything, and then I won't have time to go into the policy, but there are some ideas in parallel to what we talked about in the rapid motor adaptation work, that you sort of train a policy with privileged information, knowing the true shape of the object, and then when you have sensory information, which is in this case both vision and touch, that goes through this visuotactile transformer, and it's estimating this latent shape of the object, if you will, the ZT hat, and then that's input to the control policy. This is what I am very pleased about how the results came out. I think I started this manipulation segment with my ideological position that I believe in multi-fingered hands with tactile sensing, but that was an ideological position. So what is the truth? So here, these various vertical bars correspond to performance of the system in different sensory settings. So the leftmost is only proprioception, so knowing about joint angles. The rightmost is if you have the oracle, you have ground truth shape of the object and its pose. And what you see in the second bar is what you get with just adding vision. And the third bar is what you get by adding touch. So these are incomplete. And then if you add vision and touch, that's the fourth bar. And that takes you almost all the way to knowing the ground truth shape of the object and its pose. So this is a wonderful result, and I think that this is going to be replicated in other tasks. I mean, we have done one task, which is rotating an object. If the task is complex enough, you really do need all this kind of information. And I think we have to get with the program. I think that we can work with minimal sensing and with minimal degrees of freedom, which will be okay for simple tasks, and for some industrial settings, that's fine. But if I want a home robot, I need that full capability. Okay, which brings me to this next topic, which is like, how do we make this systematic? So in computer vision, we had a kind of taxonomy of what are the standard problems. So I used to call this the 3 R's, sort of recognition, reconstruction, and reorganization, where reorganization was the word for segmentation. And these were central problems and around which the field worked for many years, and we today are close to solving at least some of them quite fully. And now, what are the central problems of robotics? Now, I think there's probably that people would agree that locomotion, navigation, and manipulation are central. Fine. So that is good. But then in manipulation, I mean, I can just make up a million different tasks that we could work on. And how do we know that there is progress? There needs to be some canonical set of problems. So with that perspective, we tried to look at the task, the problem in a similar way to what computer vision people did for object recognition. So for example, a data set like COCO, they wanted 80 common objects. And they said, okay, let's develop a recognition system which works for these 80 common objects. The techniques will be general, and then it can be scaled up to 100 or 1,000 or 10,000 or whatever. So what are the common manual actions? So the thing is that actions are really an infinite and open vocabulary kind of thing. So then we thought that atomic actions may be the place to focus on. So like what you can do in 1 second. So then it turns out that actually a relatively small list, maybe like 20 or 24, can be made, and this is the list we made. And this covers a lot of the actions that people do with their hands. Okay, and I mean, you may not necessarily buy exactly this list, but it corresponds to common English verbs. You can look at a data set like 100 days of hands and see what is going on at the time scale of a second. So this is not about how to make an omelette. How to make an omelette has to be broken down into individual atomic actions, and this is about the atomic actions. So just to give you some examples, so this is a skill. So I'll call these motor skills. So we can do this. Humans can do this very well. We want robots to be able to do this very well. And there should be generalization. So it should work for any container and so on. Once you think about it that way, you'll realize that your parallel jaw gripper is not going to be able to do it. Here's another task, which is screwing or unscrewing a bottle. This is a common basic task. Okay. Here's another one. This is tool use, example, cutting with a knife. And so on. We have this list of like 20, 24. There might be variations that you might have. You might have slightly different ones, but I think most of the items, most of these will be common. And when I say skill, it has to generalize over a large number of objects. So I don't like this trick where basically all you're able to do is pick up, but you can pick up 50 different objects, so you call that 50 different capabilities or tasks. No, that is silly. Pick up is pick up. That's it. It's just one. Okay, and with that perspective, we tackled one of these, and this is a paper which will be presented at the next Choral, so I'm going to again play this video, and this will be, this is work led by my student Toru Lin. Okay, and So this is a very challenging problem, but we have trained it completely in simulation. And here sensing includes proprioception as well as vision. Doesn't have touch. I think it would work better with touch. And the generalization is over a wide variety of bottles. Okay. I wouldn't call this task fully solved, but I think it's a significant progress on what's a very hard problem. And what we need to see is whether this paradigm, how well does this work across like these 20 basic atomic skills. So again, the paper is on arXiv and it will be presented at Coral, so I'll move on from here. Okay, the last 5-10 minutes that what I'm going to use is to talk about the value of imitation learning. So, and here I mean visual imitation learning. This is not the same as teleoperation. I know teleoperation is like the most popular thing in robotics these days. And that's fine. I think it has its role. But with teleoperation, it's painful to collect lots of data. Whereas we have 156 million hours of video on YouTube. So if we can collect data from just visual trajectories and use that to train robots, that would be so much less painful and so much easier, because humans can just do the object. Even if you want to collect data with humans, it's much easier for humans to do it with their own hands. So let me show you what so this is building on a lot of advances in vision. I mean, the problem, I think, of 3D-fying the hand and 3D-fying the object is not fully solved yet, but we have made significant headway. So I'll show you some of the results. So this paper was presented at CVPR. So the hands are being reconstructed frame by frame. Okay, and they are essentially being detected and lifted to 3D. Anyway, you get the idea. So what I'm saying is that the technology for in images, I mean, in this case, it was done from single image at a time. Detecting the hand and lifting it to 3D, getting all the degrees of freedom has become pretty good. Okay, but what we want is hands manipulating objects. So therefore, we need to have the object in 3D as well. And this is something we have worked on before. I mean, there was an earlier paper with Ilya, and here is some ongoing work right now. And let me show you what we can do here. So here the idea is to build on some other big model called MCC, which came out of our collaboration with Meta colleagues. And that model can lift from images to 3D objects. And let's try to put these together. So the idea here is that when you have like an image like this, so this is a hand and an object. So we can lift the hand to 3D quite easily using hammer. And then you want to do the 3D reconstruction of the object. And 3D reconstruction here means both the visible and the hidden side of the object. And that's what this MCC is meant to do, 3D reconstructions of objects from single images. But this is MCC in the context of hand objects. And so that's what's being done. I mean, this paper is on arXiv, you can find it. So here are, and then of course, we can get the benefit of temporal continuity to improve the results. So these are some numbers which on various standard data sets. And I think the state of the art now is much better than it used to be 5 years ago and so forth. And it'll just get better. I mean, this is a problem which can be solved by throwing big data at it. Okay, but let me show you what one can do. So we can get reconstructions of this type. So there is an object. So this is essentially a hand holding an object, and you are seeing it from different points of view to tell you that this is a 3D story. And now, of course, you imagine this in time, and that's what we are after. And so Jane Wu, my postdoc, is working on it, and she has some latest great results. But I think of this as an enterprise which is ongoing, but we will crack it. I mean, the computer vision community will deliver on this. So robotics should start assuming that sooner or later this problem will be solved, and the question is, how will you use it for training robots? So, okay, so this is just more results. Okay, so here's a project, and this paper is available on arXiv, where we have tried to address this problem of if you can find these hand object trajectories, just visual, right, but in 3D, how do you use those for training robot policies? So, and people have had this idea for a while. So I think of imitation learning and behavior cloning as related but not the same approaches. So imitation learning, the processing afterwards is harder than from behavior cloning, but I think imitation learning is a more general approach for which data can be collected much more easily, and I mean millions of hours already exist. So here what we are doing is a hybrid approach which uses a combination of imitation learning and reinforcement learning. So essentially you can get these trajectories from imitation learning, and these can be input to a system which is in a simulator, where in the simulator you can do reinforcement learning and you can enforce physical correctness. And kind of this is the basic idea. So you have 3D hand object trajectories. You have sim in the loop retargeting, because of course the human hand is not the same as the robot hand. We have pre-training with a causal transformer. This is similar ideas to what Ilya showed, which is next token prediction kind of thing. And then we can do downstream adaptation. I mean, the dream here, of course, is that you can do this for many, many tasks and together in one big model, which then with a suitable maybe language cues can do different tasks. So so what are the benefits here? So one clear benefit is that if you were to do vanilla reinforcement learning training for those tasks, it would be very expensive and require a lot of reward hacking. It's much easier to operate on top of this representation which has been built up from visual trajectories. And the curve, I guess the R's curve is the one which shows that you need far fewer agent steps to reach a certain level of performance. And then here are some various metrics by which you show the benefit of this. So I think both the imitation learning component and the reinforcement learning component are important. It's not one or the other. And let's see, maybe this is some videos. So these are real robot results. Okay, let's look at this one. Okay, let's look at this one. This is interesting. It says 2 blocks stuck on top of each other, so a parallel jaw gripper wouldn't do it. You really do need this hand. Okay, let's see what this does. Anyway, I think by now you get the point, so let me move on. So, okay, so now this is my penultimate slide, and now I answer the question in the title of my talk, which is home robots. When will we have home robots? So I personally am much more focused on home robots than industrial robots. So there's a lot of research in robotics, which over the years has focused on industrial robots. And for industrial robots, you get some benefits and some things which make it easy and some things which make it hard. There you have this natural tendency to specialize to a particular task. Whereas if you are interested in building home robots, it has to be multi-purpose. If you want to, I'm imagining, of course, a humanoid with multi-fingered hands who can be your robot butler or servant or cook or whatever. And if that is your goal, I think we are some years away. It's not going to happen in the next 2 years. But I think we are seeing some of the building blocks. So from my talk, I would say locomotion. We can do locomotion for quadrupeds quite well. I mean, basically, I think of that as kind of done. Locomotion for humanoids, we can do quite well, but we need to do versions of this task with vision. If you noticed, our humanoid was walking blind. There should be a version of this task with vision, and it should work in really difficult terrain. So like the demo that I showed for a robot dog walking on stools, can we do that for a humanoid? And not in a canned setting. I mean, obviously in a canned setting, people have shown these results. You can find those Atlas videos and so on. So that's locomotion. Navigation is like really quite well there. And in a home setting, I think you get to explore the same place repeatedly and you'll become good at it. Manipulation is where I think the action is. We are quite a ways short of human capabilities.